So note that cache memory is very important. Topic is possibly one of the a very interesting research problem. In last say 20 or 30 years, there must have been more than 100 PhDs on this topic. How to design cache must have been more than 1,000 papers written on that, and it's very important area for people who design computers because I mean, if the cache works fine or is totally optimized, then speed of computing becomes very high. Uh, all right, say note, for example, that we have studied 5 level pipeline, right? Okay, remember that pipeline that we have studied? Uh, Instruction starting with instruction fetch stage, instruction decode, and register fetch. Okay, then execute, then memory, and then register write back. These 5 stages are, each one takes one cycle in pipeline design. Okay, and then here the memory is there in two places, right? Instruction fetch, where we fetch instruction from memory, so we call it instruction memory. And then here we have data memory. Okay, so now note that how much time we have to access an instruction or reading an instruction. So it has to be done within one clock cycle. And what is a clock cycle in general? If you have 5 gigahertz clock, that's what we are using, right? So you have approximately see around 1.4 sorry 1 by 4 nanosecond. Okay, essentially less than a clock is available for reading and writing, right? So it means that memory has to work at the speed of the clock. So and you have seen that processor is speed versus main memory speed. I mean, if this is one cycle, this will be approximately 1,000 cycles for simple one data item to read. And this gap is huge, and hence we put in between a cache. Okay, now if cache, it means that cache now has to support processor at that speed, right? So cache has to work at the speed of the clock, or actually the response time from cache has to be less than that of a cycle, right? And what happens if there is a miss? If cache does not have anything, it has to bring it from main memory. So does it mean that processor has to wait 1,000 cycles? Yes. So if the processor has to wait for 1,000 cycles, imagine what kind of penalty it has. A huge amount of wait time. So a whole pipeline has to be stalled, and that's not good thing. Okay, so that's the reason cache have to be very fast, very responsive. It means the access time has to be very small. Okay, all right. Okay, no issues. All right, so that's very important point, that memory, the whole cache, that's the reason, as processor speeds are going up, it has been going up all throughout in last 20-30 years, and then more and more computing we are doing, and memory speeds are not growing up. So every time people have to really work on simulations and research and so on to design cache memories in such a way it improves the performance of the whole computer. Okay, All right, with this idea in mind, let's start. Let's look at the some real world chip photos. So this, in this processor we can see this is a 2-core processor, and then caches are shown right here. So it means that each core, when you are using multi-core processors, because today most of the processors are multi-core processors, whether it's a mobile or laptop or server, then each processor, if it is multi-core, then each core has got to have a cache. Okay, so here it is shown how many, what levels of cache it will have totally depends on design, whether each core will have a single level 1 cache, or it will also have level 2 cache, and so on. Totally depends on design, right? But processor cores have at least one level of cache. Okay, and you can see here in this, another chip, that here we can't see really where the local cache is, but we can see that L3 cache is shared among all processor. Okay, usually level 1 and level 2 and level 3 caches are shared. Sometimes level 1 and level 2 are in the core. Okay, uh, so here we can see in this processor L3 is shared. All right, let's now start with what we have studied last time. We have seen that there is a need for cache because the processor operates at very high speed and memory is in general slow, 1,000 times slower, so we need cache in between. Now note one thing is that something that is be on the right hand side is processor is not really aware of that. Okay, okay, although the process, so in some sense, okay, it's like this: when you do load instruction or store instruction, do you write that it's going to cache or main memory? So simply write load word to some register, say S1 contains you know okay, some, basically some offset, and some contents of register, say S2, which is a base register. Okay, all right, so where does it say that it is for cache or is for main memory? It doesn't, right? So it means that for processor, view of memory is just that of address space or main memory. That's it. And when this instruction is issued, is in between, it's intercepted by cache, and cache will see whether this data item that processor wants is available. If it's available, it supplies it. If it's not available, it gets it from lower levels. Let's assume there's no lower level, it's only cache and main memory, then gets it from cache, gets in main memory, and then cache supplies this to processor. All right, any question? Okay, so note that the cache is invisible to programmer and to processor. Okay, now that gives us advantage because it's kind of invisible, then we can change the cache design the way we want. All right, and one more reason, you see that see, when we discuss ISA, we never discuss about cache. So ISA for Intel or ISA for the instruction set architecture for RISC does not say what levels of cache. It is left to the implementation. So this is part of microarchitecture. Okay, all right. So this example we have seen that cache here is 1/4 of that of a main memory. And something we discuss is that each cache has okay, blocks, right? So we can divide memory into number of blocks, and each block in main memory is mapped to exactly one block in cache memory when we are doing direct map cache. Okay, all right. So then we have seen that this is the main address that comes from processor CPU. Okay, and this one here, which is index, gives us the location in cache or index in the cache where the block is residing. Okay, so here we had 16 blocks mapped into 4 blocks. So these bits in the address, because this the whole address corresponds to a location or a byte somewhere, and this byte is part of the one block. And if that block is here mapped to exactly one block in cache, then that location of that block is given by index. Because there can be, so when we say many blocks can be mapped, in this case 4 blocks will be mapped from main memory to cache. So now we need to find out which of these 4 blocks that can potentially be mapped to this one. Totally depends on what is these tag bits, right? So these tag bits here or higher level bits differentiates between various uh, blocks that can be mapped. Okay, so the particular block, suppose this is available here, then we will have to add tag bits here. Okay, and then this tag bit, when it's will if it matches with the address that is issued by CPU, then we know that this particular block is available. Okay, so this we have seen in the last class. Then we have seen this index, tag bit, and offset. And offset is nothing but offset within the block that we have brought in. Okay, with this knowledge, let's take up another example. Then we'll move into set associative memories. Okay, uh, take very simple example. Okay, now the points here discuss the same thing, that first we look at the address that comes from memory, is from CPU. Then in that we know what are the tag bits, because it's implementation dependent, because this address is intercepted by cache controller, and it knows what are the tag bits. So it will look at the tag bits. For example, there are 2 bits for tag. It will look into the tag store, okay, and find out if the tag is there and then valid bit is there. We have seen that there's a tag bit and the valid bit. So we have this structure. We have block, okay, then we have tag, and we have v bit. Now v bit has to be valid, because in the startup time v bit the block here may not be valid. So and there are many other reasons for valid bit, which we'll discuss maybe later. So first thing that it does, it checks for tag. Okay, and if tag matches, I'm sorry, I'm so sorry, I'm sorry. So first thing it does is that it looks at the index bits and goes to because there are many such blocks, so goes to right uh, entry, right, and then it checks tag bit with this bit that's available, and if it matches, also looks at v. If v is also valid, then it can read the appropriate byte from here, the block. Okay, this is a flow. So I will repeat one. I will repeat just a minute. Okay, okay, so it gets this address from CPU. It looks for index bit, okay, goes to cache and goes to appropriate block, okay, because index gives a block number, and then in that it looks for tag bit. Okay, if this tag bits here matches with the incoming tag bits, okay, and then V is also valid, then corresponding data can be read. And this offset, which byte we have to read, is given by the offset here. Okay, so simple. Let's look at the example now. This is very similar to what we studied in last class. Now let's look at the example where we have 32 blocks. Okay, so we are mapping. Okay, okay, this is 32 blocks, right? So block 0, block 1, block 2, block 3, block 4, block 5, block 6, block 7, block 8, and so on. Now the one we have shown green, essentially we just to differentiate that this green will be mapped to the first block. Okay, so and then each block is of 8 byte. Okay, so there are 32 blocks, each block is of 8 byte, and there are total number of bytes is 256. Okay, okay. Now this is mapped to 8 blocks of so total number of bytes are in the cache memory is 64 bytes because each block is of 8 bytes. Note that the block size for main memory and also for cache is the same. So this is a cache. So we can see that there are 8 blocks. So this is block 1, block 2, 3, 4, 5, 6. Somewhere I missed 3, 4, 5. Okay, so 0, 1, 6, 7. Okay, so these are basically 8 blocks. So these are to be mapped into, when we say direct mapped, it means that if we read say this one, okay, then looking at index bits, which are these index bit, okay, we can know it is mapped to say this one, 0, 0, 0, first one. Okay, so so that's now once we know that from the index this particular entry, then we look at the tag bit here are the top 2 tag bits, right? So if so here in this case is 0, 1. So once we fetch this and it happens to be 0, 1, then we know that, and the valid bit is 1, then we know this data is something that we can, this is right block, valid block, and we look then the offset. Now here of course we have not shown offset here in the address because this is a block address. Then we can see the offset bit that comes from CPU and then take out the whatever byte is required. So is it clear? Note that all these shown in green with block address 0 will be mapped here to this one, this entry. And then we'll have to find out which of the 4 is actually available. That can be done by matching the tag that's available here with the tag that comes from CPU. All right. Any question? Okay. I hope it's clear, right? It's simple.
सर आई हैव वन डाउट.
हाँ बोलिए.
सर वो जो टैग है सर, टैग की बिट्स क्यों नहीं काउंट कर रहे हो आप?
कहाँ पे?
सर ये जो इसकी साइज है कैश की, एक ब्लॉक की 8 बाइट आप ले रहे हो.
Oh, tag is not. See, what happens is that now I am showing this data element, right, block here and tag together. Okay, actually data store and tag stores are different. Okay, so basically data, so because data store has continuous data items, it cannot have in between tag. Okay, so we will actually, in fact I have created this diagram for simplicity. Some authors use it this way, some authors say that there is a data store, exactly same number of entries as tag store, one-to-one correspondence, they are kept separate. Okay, because obviously it cannot be part of the same memory because the data here is all linear, right? Similarly it has to be linear. So that now what you do is, this is tag store, the data store. Okay, and then you then if through index you search into tag store, okay, and tag matches, then tag matches and valid bit is also there here. So if valid bit also matches, then go to use that index. It means that there is hit, and go to data store and then read. That's the reason, we when we said, see, we can treat this as an overhead, but in implementation these are implemented separately with one-to-one correspondence. All right, got it?
Yes, sir.
Okay, so treat this as a when we say data actually is a block. Okay, so apart from that there is some overhead, and this overhead can be substantial if block size are smaller. Okay, so those are efficiency issues that we may consider later, but no one really talks of overheads of memory because of tag, because when memory is extremely cheap, it doesn't cost much, right? Of course cache is expensive, but cache is smaller in size, so very few tag bits will be used there. Okay, all right, good question though. All right, so let's come back. All right, so this is the one. So we can see that using index we can first go to tag, take out the tag entry, and if it matches with the entry here matches with the up, it's gone. Okay, entry matches here with tag bit here, then we have hit, then correspondingly we can read appropriate byte. So the diagram is follows. uh, Implementation is follows, right? So first you get the from index has to be used first. You get the tag value. Okay, so you from this store you read the tag bits come here, for example corresponding to index. For example, index is here, so these tag bits will come here. Match it with the tag that you are getting from CPU. If both match, then there is a hit. If does not match, then there is a miss. Okay, and this is a comparator. Okay, and then if there is a hit, then you look at the offset. Okay, and of course you index is the same, so use the same index to get to point to this one, and use then offset to find out this byte, because it's a byte addressable memory, and you can read that. Now implementation is follows. Okay, now using okay I need to clean it up. Okay, using index bit. uh, okay, implementation is follows, right? Using index bit, of course we have done the tag match, so these two things will happen parallelly to save time. So whether it's a hit or not, get the tag bits, and at the same time these bits are available, so match it. Whether hit or not will come to know. At the same time use this index, and then read the complete block. Okay, bring it to mux, and then use the offset that's coming shown as green is here, and then select the appropriate block, appropriate byte. Okay, now if now next step that we have not shown here, if this is a hit, then this data is valid. So actually we can have one more mux, output is going to that mux. Okay, and if this hit, then data is valid, otherwise just ignore the data. All right, get it? Now what happens? Now I will give a scenario. What happens now? This works beautifully if only one of the blocks is in the first location, right? Or maybe and then second one has one of these which ends with 001, this one or this one or this one or the one in the second one. And similarly third block is reserved for one of these 3, right? 0 1 0, 0 1 0 here, similarly here and here. Okay, only one of these 4 blocks can come in third position, and so on. What happens if your memory wants, or if your CPU wants this block and the block here? Because only one can be in this particular location. Okay, so that kind of, so once we are using this, and we want this one, basically we are fetching data from the both, then only one can be there, right? And this kind of miss, we call it conflict misses. So the address with the same index, index bit is 0 0 0, for example, for first, for the block here. So 0 0, if this block or this block green, third block or fourth block, if they contend for the same, because all these will contend for the first location here, then there will be conflict misses. Only one of them can be here, right? How to improve on this situation, we'll see. Now this is another view. I like this view, and it's given by this lovely book by Bryant and Helleron. So I brought it here. I made some modifications to that. So note that we are showing the same thing here in the following way. Okay, so these are the 4 blocks. Okay, and these are the bytes inside, because we say there are 8 bytes per block. So there are 8 blocks. Okay, first, second, third, up to 8. Each is having 8 bytes, and then we have tag bits, which are 2 bytes, and then V bit. All right. Now note that we are using slightly different terminology here. We can call each block also as a line. Okay. The question you asked just few minutes back is relevant now. So block is actually, in terminology, is nothing but that contains the data. Okay, and when we add to that tag and V, the whole thing is called line. Okay, this is IBM terminology. Okay, now nevertheless, in our discussion we'll use line or block interchangeably. For us, both are the same thing. Block actually contains the data items, and we can assume that along with it, it has overhead of tag and V bit, validity bit. All right. Okay, so this, and then this each block we should also call it set. We can say set 0, set 1, set 2, set 3. Now each set here has only one block or one line. Has one block or one line, whatever you may want to call it. Okay, all right, so this mapping is clear to you? Okay. Okay, so we use, now note that we use index to point out to the right one. Okay, right block here, or right set actually. Okay, and then we use the tag bits that are given, because this is coming from CPU, to match with the corresponding tag here. Okay, and if the V bit is set, then we look at offset to find out which particular uh, byte we have to read. That's very simple. Okay, so now let's look at, of course this is the same thing that we have discussed. What is going to be the cache size using this kind of terminology? What is S? S is number of sets. How many sets we have? We have 8 sets. Okay, now how many E is how many number of blocks we have, or now how many number of lines we have per set. So we have one block per set, and each block has how many bytes? 8 bytes. So we have total 64 bytes. So, okay, this is how we calculate. So exactly same thing we have written here. Okay, all right. So now with this example, now this address comes from CPU 01010011. Okay, when it comes, then cache controller knows what are different bytes, different bits in that refers to. It knows that first 2 bits are tag, next 3 bits are index, and the remaining 3 bits are offset. Okay, then first uses the index to go to appropriate set or appropriate block in this case, and then matches the tag. Okay, uh, here and here both are the same, then uses this to read the offset. Okay, all right. So this is how it is. Okay, all right. Now here note the number of sets is equal to number of blocks. Here, right? And we also know that there is a conflict. If the 4 blocks that we have seen in main memory earlier example maps to same thing, then there is a conflict. Only one of them can be there, right? And this can increase the misses. So what we do is that, why not 2 of them be there in one index? Okay, so now the misses may reduce this way. Okay, so one example we can see is, okay, this point we have discussed. Now if you are using just 1-to-1 mapping, right, these 4 are going to map to only one location. So we can also have a scenario where there is a 0% hit rate. Okay, initially, for example, uh, if we have 2 addresses A and B, okay, and these are corresponding to different blocks, but those blocks map to the same index in cache. Okay, like we have seen in earlier case, uh, sorry, okay, uh, here if one address is from here, one address is from here, and a second could be from there, then there is a problem, right? So how can we improve on this then? Yeah, just a minute. Okay, so what happens is that if one address is for first block, second address is from second block that with the green color, we say that both map to same location, and the memory access like this: a b a b a b a b a b a b. Initially nothing is there, so there is a miss. Okay, now A has brought in to cache, and then there is a request for B. Now B block, which is in memory, will also the block corresponding to B will map to the same cache location. So it means that A will be evicted and B will be brought in. Now the next memory access is corresponding to A, which again belongs to the block which was earlier in the cache. So in this way, we will have continuous conflict, right? And the misses are conflict misses. However, note that the advantage of this scheme is that we are using only one comparator. And also note that because of one comparator, delay is less. So as many combinational circuits you are adding, then your critical path is increasing. And whole idea is that you have to reduce the critical path, because within part of the cycle you have to do the reading. Okay. Hence comes the concept of set associative memory. So we have seen the address 0 and 8 always conflict into direct map cache. So instead of, now we had a column of 8 in cache memory, we had 8 blocks one after other. Okay, and then 4 blocks were mapping actually to the same location. So why can't we do it in such a way that we have 2 such blocks in one index? So now number of indexes will reduce to 4, these entries in the cache, index entries. Okay, it will be only 4. However, there will be 2 blocks. Now these 2 blocks, you know, will corresponding to an index. Okay, so now number of index bit will reduce, but at the same time, number of hits will also reduce. Okay, so it will handle the conflicts better. However, is a more complex and larger tag store. Let's look at the diagram now. Okay, so we call it two-way. It means that each set or each index has not 2 blocks. So one block here and second block there, and of course this is tag bit, this tag and the v bit here. Okay, so now note that the cache size is same, but we have each index location or each set that's pointed by index bits will be reduced to half, but each index or each set will have now 2 blocks. Okay, so now we will, so number of index bits will reduce by 1 here, so we have 2 bits because there are now 4 entries here in the cache. And so this first we'll use index bit to find out where in cache we are pointing to. And then what is the next thing? Now both tags have to be read together. Okay, oh, it's not shown here, but should be like this. Okay, so both tags will be read, and then it will be then matched with the tag entry that comes from CPU. So the one here, same thing will go to second one is there. Sorry, I'm sorry, tag is coming here. Okay, let me just clean it up again. Okay, I didn't see that line. So this tag, okay, first use index to point out the entry, then both tags are to be read. Okay, so this tag one comes here and second tag is read here. Okay, and then compare it with the tag that comes from CPU or the address, and then we do matching. Okay, and if the valid bit is set, valid bit comes from here, wherein second valid bit for second block comes from here, and then we'll find out whether it's hit or miss. It's a simple combination logic. Now the data is at the same time taken from both blocks. Okay, and then based on the hit one, if it is a hit one, or this hit corresponding to this one, then we'll select this data, otherwise other data will be selected. Okay, and if both are, if obviously there will be hit for one, so a hit could be one. Okay, if there is both are 0, it means there is no hit. Okay, then we can hit bit here will be 0, and we can use this hit bit to invalidate the data that has come out. All right, so is it clear? Any question?
Sir, I didn't understand how we are able to reduce the number of sets and still have all. Still it's working, because now we can't have 8 different indices, no, which can be stored
No.
in the
So
cache.
let's look at this diagram. Okay, we have put, so we had essentially the block size is same. So earlier we had 8 blocks, one after other, right? Okay, now we are using, only thing is that now you are using 2 bits for index, because these are 4 columns or 4 sets. Earlier we had 8 sets of 1. Now there are 4 sets of 2. Okay, so we can use, now earlier we had 3 index bits, so now we have 2 index bits to find it out. and offset is the same because we are using 8-bit blocks. Now tag bits have gone up. Tag bits, earlier we had 2 tag bits, now we are using 3 tag bits. Okay, so let's look at the example. Okay, all right. So first we'll use this index to find out set. Then we'll compare tags. Each one tag we'll compare. For example, if this set is selected, this tag and this tag is taken, is to be compared with this tag. Okay, and if valid bit is, let's assume 1 in one of these, and the corresponding output, if this is, if these are both, you're doing AND here. So if this is true, it's matches, and this is 1. Then if this is valid, then we'll look at offset and find out whatever is the location of the byte and read that out. Okay. So this simple example, let's take up this example now. So now this address comes from the CPU, and we have a structured block which is two-way associative, means that each set will contain 2 blocks. Okay. Now look at the advantage of having this structure versus the earlier one, because let's assume that where the conflict was the first block and then 5th block, if both were contending earlier, because index was the same, then there would have been conflict. Now if in this case we can bring both of them here, okay, if the 2 blocks want this, all right. So the advantage is that we are reducing the misses here. All right, so now look at this way. The number of blocks are the same and offset bits are also same. Okay, but there are 4 such, just let's go to previous one. Okay, there are 4 such blocks, right? 4 such entries or 4 such sets. Okay, so we need only 2 bits here. Okay, all right, and then we'll need larger number of tag bits, because now we need to, because we'll have to see how many, tag bits actually is coming from in memory, because how many such blocks are mapped to a particular location. Okay, so using these things we can find out exact byte that we want to read. Any question? I mean, is it becoming clear or is it still confusing? So this is the first structure that we are using, right? Second one, what we are doing, the number of blocks are the same. Okay, number of the blocks are the same. Okay, but what are we doing? Instead of 2 bits, we are using 3 bits for tag, right? And 2 bits only for 2 bits only for so first 2 bits are used for index, and remaining 3 bits are used for tag. Okay, so we'll have to now see that how, and the one with how many positions are there with these 3. So basically 8. So like we have 4 green colors, now we'll have 8 such green colors. Okay, okay, and then each, just treat this as a green color, the one which is shown as double line here. Okay, now each, and now the structure is as follows. We have 4 sets of 2 blocks, right? So it means now any one of the 8 can come here in the beginning. Let's say the memory reference is corresponding to this, it comes here, and now any one of the remaining can come to other place. Let's say the memory references to this one, it can come now to this place. Okay, so can you see the difference? Earlier we had this structure, 8 of these, and then actually 4 were competing for one block. Now here we have created 8 such things. 8 blocks are competing for 2 blocks. So 4 are competing for 1 versus 8 are competing for 2. Okay, does it make simple? Now what happens is that because of this, and if this block happens to be say here, and then memory reference is corresponding to this, then now number of hits will increase. All right. What I suggest is just start, just visualize this, what exactly is happening and how is it really reduce. Okay, we are basically we have same number of blocks in main memory as well as in cache. Only thing is the way we organize is different, and the way we bring the block from main memory to cache. So as we increase the associativity, the memory becomes, cache becomes more and more complex, because you will have more number of comparators. Okay, for example, here in this example we will have now 2 comparators. Just a minute. Yeah, we have here 2 comparators. Okay, so overall it will become more complex in both in terms of cost and design and delay. Now what is the next step? Can we have fully 4-way associative cache? Now let's have only 2 blocks, 2 sets, and each set is having 4 blocks. Okay, so now how many so index set is selected using index, so we just need 1 bit. Okay, and offset within block remains same because 8-byte block. Okay, now tags are gone up. Okay, because number of blocks that are going to map to this index will go up, it will double. Okay, from the previous case. So we need 4 bits to represent tag here. Okay, so we call it 4-way associative cache. So it will look something like this. Okay, so we'll first use index, only 1 bit, to find out which of the 2 it will point to one of the 2, and then we all these tags. Okay, so will be compared with this tag that's coming from CPU, and then the one which matches and the valid bit is also set to 1, then we'll read using offset the corresponding byte. Okay, so it's look at this way, is that it's a different way of representation. So here, how many such blocks are mapped to these 4 blocks, which can go anywhere? So 2 raised to the power 16 such blocks in main memory are mapped to these blocks 4 or this set in the cache. Okay, and any one of these, if referenced by CPU and if it's available, then it can go to respective. The second, for let's say this, the first one will come here, second will come there, third will be there, fourth will be there. Out of any of these 16 can come to these places. Okay, and that's how we call it associative memory, because here we'll have to compare this content of the memory, content of this memory, which is tag bit, is kind of matching we are doing. Okay, of course the size of the cache remains the same. The only difference is number of sets now reduce, but number of associativity within set doubles, right? So instead of 2, now we have 4. So number of set is 2, number of blocks within a set is 4 and number of bytes within a set is 8. So that becomes 64 bytes. Okay, all right. Can we increase the associativity further? So the previous example, this is how we are doing. If the address is, for example, that comes from memory, sorry, that comes CPU 0100 01100, use the index to find out which of the two sets, and then match all tags here with the tag here, and we'll know that this tag will match. Okay, and then look the offset and then read corresponding offset is 100. Up, it should be 4, not 1. So instead of this, we'll read this one. Okay, all right. Or we can change this to 001. All right, and then from this one, we come to the here diagram where this is a fully associative. All 4 sets are in one set. Okay. All right. Now we will have 5 bits to represent a tag. And index, because there's only one set, the index will be 0, and there will be byte offset. Okay. It means that we don't use index here. And then we simply, as soon as this comes from CPU, start checking all tag bits, whether it matches. If it matches, then, say for example, this one matches, then there's a hit, and then look at the offset bit and read corresponding byte. But number of comparators here will be 8 now, because each tag bit, each tag will be compared simultaneously. Okay, so this will increase the complexity and the cost. So it's shown like here. Okay, all right. So is it becoming clear to you, or is it not so clear? So if you take up the diagram, for example, let me go back. Oh, it's almost 1 hour now. We are still, I don't know how much time will take more. But this concept is very important. Okay, in this example, what will be? Now here we have taken, example is the same. Let's assume that we are taking 4 blocks of that set 1 set, this second set 0 and set 1. Okay, then what are we telling? There is only one index bit. Okay, that we'll use here. Okay, and then offset bit remains the same. So this is block address 00000 block address, and then we have 3 offset bit. We'll just ignore at this point in time. Now what are we doing in this case? We have only one index bit, so this is the only index bit, and then these are the 4 other tag bits. Okay, and then how is this structured? In fact, it means that now 16 of these, so we'll have to, instead of 4, we'll have 16 such, every second blocks will be of green color. So let's assume this red color, this also be red, this is red, this this and so on. Okay, all this will, whatever red color we have, which are 16 red colors, and 16 we can have some other color, that's a green color. So all 16 red will match to these blocks can potentially go to this place, and all the remaining 16 green will go to this one. Okay, and there are only 4 positions here, so 16 will compete for 4, and this green 16 will also compete for 4. So we are actually, the way we are structuring the whole cache is different. Main memory remains the same. It's just left to you how do you interpret green and red and so on. Okay, all right. Is it clear or not? You need to just go through the PPT that I've sent and try to spend some time. It does not come intuitively very easily. Okay, that's the reason I have taken almost 2 classes to explain this concept. However, this requires you to do some reading. You can do the reading from the book or the PPT I'm sending, and try to see, try to play with it, try to play with bits. Main memory remains the same. All, you know, the block size in main memory remains the same. Block size in cache memory remains the same. Now this left to see that how many blocks in a memory are getting mapped to one block, or we can say set number of blocks in memory are double number of blocks are getting mapped to 2 such blocks in cache. So when we are saying that initially say 4 blocks are mapped to, you know, 1 location in the earlier example, and now we are telling that, you know, when we double the associativity, instead of 4 we say 8 are mapping to 2, and if we increase the associativity to 4, then we are saying 16 of that are getting into one set, right? So it's essentially the 4 to 8, 8 to 16. That's how we are changing. And then in the last case, all 32 blocks will be part of one set. That's called fully associative. Okay, so just a minute, we'll just come to that and close today's discussion. And I would request all of you to please go through the presentation, right? All right, so this is fully associative. All right. Okay, all right. Okay, we'll stop here and we'll again we'll start from here tomorrow. Okay. Anybody, please let me know if you have a question, and remaining people can leave.
Sir. Hello.
Yeah.
Sir, like we had the direct mapping cache we were doing, like there can be like this way, like we have a hash map, and probing, by probing we can like optimize that thing.
Yeah, so why we are doing that, we'll study that, right? Because initially what we are doing, we are mapping only 4 such blocks to one position. In second case, when we increase the associativity to 2, so actually we are mapping 8 to 2 positions, 2 blocks. And what are we doing? Further increase associativity, you know, then instead of 8 we'll map 16 to 4 blocks, and increase the associativity further, you are mapping all 32 to 8 blocks. Okay, yeah, 8 blocks, right? So essentially it means that 32 are mapped to 8. It means that any one of the 32 can occupy first place. Okay, let's say first block is gone from the cache, then any one of the remaining 31 can take the second one, any one of third, the 30 block can take third one, and so on. That was not the case earlier. That was, they say, only one of the 4 with certain addresses can take up first block, right? So we are increasing the flexibility here. Okay.
Yes.
Okay, so please go through it and play with it, because it, you know, I mean, honestly, I mean, it took me almost 8-10 hours to read it from multiple books to make this presentation, because I thought this is very interesting and important concept. Okay, and I will also request you to go through the video lecture by Professor Asinovic. If you search in the YouTube, Professor Azinovic's talks, you'll get it, because those guys are really brilliant. Possibly we'll get some inputs from there. I'll send you the link for that YouTube talk. In fact, this content is available by many authors, right? Even Briand's explanation is quite nice. All right, okay. Please go through the presentation, and tomorrow we'll try to finish everything about cache, because this will be 4th lecture. And please ready to come for 2 hours at least. Okay, we want to finish cache because we have only say 8 classes left out, less than 8. So we want to cover other topics as well. We'll do memory hierarchy, and then we have to do GPU design and so on. Okay. However, this particular part requires you to do reading and playing with numbers. Okay. All right. Thank you.